students. So our main intention is to inform KPA members as well as students about developments in various fields of physics in the most convenient manner, that is the online mode. We also wish to connect all, one of the other objectives is to connect all physics teachers and faculty in the state in some kind of a network so that they can come to know which are the fields being represented in the state and so on. The topics selected are meant to introduce the participants to new fields that may not be familiar to them, like what we have today, quantum science and technology. And we have also conducted talks in Kannada, the regional language, with the objective of encouraging effective and efficient communication between students and teachers. We all know how difficult it is for students to communicate with teachers in a efficient manner. Even the teachers also fail in that direction, I suppose. So Atmanirbharta really means ultimately we should be teaching and learning in our own native language at all levels. Okay. So that may not be possible immediately, but we should make an attempt, and we are doing that in this series of webinars. So we have been helped in this endeavor of ours by faculty members of colleges, universities, and research institutes. The webinar is also telecast live in the YouTube mode for the benefit of students, other students, school students, and the general public. So today we have Dr. Sudha from Kuvempu University, who is going to talk about the basic aspects of quantum science and technology. So join me in welcoming her to this seminar on behalf of KPA. So before I request her to speak for about 15 minutes, I request our Joint Secretary, Dr. Rudraswamy, to briefly introduce the speaker. Over to Rudraswamy.
So thank you very much, sir, for this great opportunity. It gives me an immense pleasure and privilege to introduce Madam Dr. Sudha, Professor, Department of PG Studies and Research in Physics, Kuvempu University, Shankarghata. Madam obtained her PhD in Physics in the year 1999 from University of Mysore. Joined Kuvempu University as an assistant professor in Physics in the year 2006 and presently serving as a professor of Physics. Awarded DC Pavte Memorial Fellowship to carry out postdoctoral research at University of Cambridge, UK in the year 2010. Area of research, polarization, optics and quantum information science. Published more than 50 research papers in reputed international journals. Guided 6 PhD and 3 MPhil students. Served as co-investigator of a DST-funded project Quest for the year 2021 to 24 and successfully completed. Presently serving as a principal investigator of a Q Pragati project funded by Government of Karnataka. Served as the coordinator of PTTS 2015 workshop sponsored by various prestigious research institutes of India. Served as chief editor of Kuvempu University Science Journal in the year 2021. Published an article on Science Need Women in the commemorative volume brought by Kuvempu University in the year 2012. Published few biographical articles in Kannada on scientists. With this brief introduction, now I cordially invite Professor Sudha Madam to deliver an important talk on quantum science and technology, a bird eye view on origin and development. Over to you, Madam, and thank you very much.
Thank you, Professor Rudraswamy, and I must thank Professor Kadli for giving me this opportunity and the whole of Karnataka Physics Association. You people are doing a great work. I'm glad to serve in a little manner, whatever I can, through this lecture and also in any other possible future situations. Okay, with that, I'll start my talk. It's on quantum science and technology. I'll start with a brief history of quantum science first, and then go over to the technology part, though not quite in technical detail, but a bird's eye view, as I said. The beginning of quantum science, the end of 19th century, It's called first quantum revolution, as you all know. There are three stages in the development of quantum mechanics. The first stage is 1900 to 1912. It's the heroes of that period are Max Planck and Einstein. Second stage is 1913 to 22. The sole hero is Niels Bohr. And the third stage is 1923 to 27. There, the quantum mechanics actually, the real quantum mechanics actually began. Yeah, this is just a history, and I'm sure all of you are aware. Like here, I want to actually tell you about the complacency of the scientists at that time. They all believed that, most of them believed that the nature has already been explained through the so-called classical physics. Classical physics is nothing but classical mechanics, classical statistical mechanics, and classical electrodynamics. But the new discoveries towards the end of 19th century, the radioactivity, X-rays, and electron, they couldn't be reconciled by the classical physics. In fact, this is a quote which I want to mention. Okay, actually, Max Planck's teacher, John Philip, Max Planck wrote to him asking whether he can take up a career in physics. This is the reply to Max Planck. Why do you want to ruin your life? It's already finished. Is it worthwhile taking up a job which doesn't hold any prospects for the future? This letter reflects a belief held by scientists at that time. They believed that a final description of physical phenomena has already been arrived. In fact, any complacency is not advisable. Nature laughed at their complacency, and in fact, Max Planck himself came over that belief of his mentor and teacher. Yeah, I mentioned about the few discoveries which couldn't be reconciled with classical physics. And it's a period of crisis in physics because these were the phenomena: black body radiation, photoelectric effect, line spectrum of hydrogen, specific heat of solids, dependence of, in fact, the structure of atom itself was not at all known. Despite that, scientists believed that they knew everything. Okay, yeah. So that being the case, I hope it's completely visible. My slides are completely visible.
They are visible. Yeah, they are visible.
Yeah. This is the famous Planck's formula and his constant H. Small detail. Actually, one of the experimental friend, a friend who was doing experimental black body radiation, like he was studying black body radiation, Dr. Rubin, he and his wife had visited Max Planck for a cup of coffee in the evening of 7th October. He told, like, he just detailed Max Planck about the Rayleigh-Jeans law. It was believed by Max Planck that Wien's law explains the black body radiation. The experimental result that in the lower frequency region, Rayleigh-Jeans law, the black body radiation satisfies Rayleigh-Jeans law, was then, just then, was experimentally observed, and Max Planck was surprised. And in an effort to reconcile with the both limiting forums, he arrived at his formula, which is, at the beginning, it was empirical. And then he came out with a theory that, and here I need to mention, 7th October is the birthday of Niels Bohr. Niels Bohr was a young 15-year-old boy when quantum mechanics opened its eyes. Yeah. Then Max Planck came up with his theory saying that the absorption of energy takes place in quantas and H is the, like, E is equal to H nu, etc. So he presented his paper at Berlin Academy of Sciences on 14th December. In fact, it can be called birthday of quantum mechanics, and Max Planck, the father of quantum mechanics. But Max Planck himself was not convinced about his quantum hypothesis. Many scientists too then. Einstein came to the help. In fact, before photoelectric effect also, Einstein had arrived at the corpuscular nature of light, again, while studying the black body radiation in the high frequency limit. In the high frequency limit, the electromagnetic waves, they behave as corpuscles, and in the low frequency limit, they behave as waves. Even Einstein later also, he studies black body radiation. And photoelectric effect, everybody knows. Here I wanted to just mention that it is not Einstein who named the photons as photons. It was given, the name was given by G.N. Lewis much later. Yeah, Einstein again contributed to the quantum nature of not just photons, also of atoms in a solid. And the low temperature behavior of specific heat of solids was explained by Einstein by considering atoms in a solid as quantum simple harmonic oscillators. This also everyone knows. Later, Debye comes with a proper formula. Einstein did explain the lower temperature behavior. The exact behavior later was accounted for by. Yeah, I said, again, Einstein worked on Planck's law, and he comes up with, it's a sum of two terms, one of them corresponding to high frequency, and that is due to particle nature, the other corresponding to low frequency, which is due to wave nature of light. Also, he comes back again studying the Planck's law. During 1916, he comes up with a new derivation of Planck's law, where during spontaneous and stimulated emission in the laser phenomena, he introduces his famous A and B coefficients, and he arrives at a new formula for Planck's new derivation of Planck's law. Einstein studies Planck's law in 3 different circumstances, each time coming out with a rich result. And okay. And the second stage, is there anything? Okay. The second stage of as I mentioned, the second stage of the development of quantum mechanics, its journey towards atomic model, and all of you are familiar with soon after the electron, J.J. Thomson himself come up with the plum pudding model. And then these are Giger-Marsden experiments. Both of them were students working out alpha scattering. In fact, Rutherford advises them to carry out alpha scattering experiments. And on several metal foils, they do conduct the experiment. It was gold that gives them, because it's heavier nuclei which recoils the alpha particles well. And the gold foil alpha scattering gives the result that there is a nucleus. Yeah, Rutherford himself comes up with a planetary model of atom, which again is a failure. Almost there, but not quite there kind of a thing. Yeah, atoms are not stable if we do not consider stationary orbits. Electrons revolve around the nucleus, giving out energy and fall into the nucleus kind of a thing. As I said, it's almost there, but not quite there. Bohr comes then, 1913. He comes up with the idea that there are stationary orbits which do not radiate. There is the idea, and he comes up with his quantized energy levels. And this is the formula which is quite well known, and it matches, like it's such a thing, though it's not entirely quantum. Bohr uses both classical formula for angular momentum as well as the quantum NH cross kind of a thing. Still, he comes up with that is the ingenuity of Bohr's idea. And he gets Nobel Prize in 1922. Presently, it is called old quantum theory because it's like, as I said, it has some lacunae. Then soon after Bohr's model, we all know it is Franker's experiment. He gets, I mean, it's such a ingenious experiment. And then Sommerfeld elliptical orbits, space quantization, Bohr's correspondence principle, Stern-Gerlach experiment, etc. And the third stage of quantum, yeah, these are the three people whom we should bow for the present day quantum mechanics and everything that we are living in. The growth of quantum mechanics, 1923 to 27, Compton. Compton's actually after Compton's scattering experiment, the wave particle duality of radiation was established beyond doubt. Einstein established the wave particle duality of radiation, but people believed that while traveling, light behaves as a wave, and at the when it interacts with matter, it behaves as a particle kind of a thing. But Compton effect proved it otherwise, and this is the it establishes the wave particle duality. Yeah, then comes Louis de Broglie, and it's a very logical thinking. Why light alone has a dual nature, matter too has, and it's a simple formula. Everyone knows it is lambda is equal to h by p, and confirmation through electron diffraction experiments. Davis-Germer experiment, it not only illustrates that electron diffracts like how a wave does, but also proves the de Broglie formula. They actually evaluate through the electron diffraction experiment that the wavelength of the electron is related to its momentum by the de Broglie relation. And G.P. Thomson, and here, I mean, I'm sure all of you know this thing. J.J. Thomson discovered electron as a particle, and his son, G.P. Thomson, showed that electron is a wave too. Both were correct, and it's a famous son and father-son duo, one among the many. Yeah. Here comes this actual quantum mechanics thing, which belongs to the 2 years of what should I say? It's a very, I mean, it goes beyond worlds. It's just 2 years, and the whole of quantum mechanics, almost all of quantum mechanics was born. During May, June 1925, Bohr was thinking of the, Heisenberg was thinking of the Bohr model of atom, like why stationary orbits, etc., etc. He was in isolation due to hay fever, and he thought about the concept that electrons' position and momentum are kind of arrays, each entry corresponding to transition between two different amplitudes. Transition amplitudes are the elements of an array, was the idea by Heisenberg. And he didn't know what a matrix is then. Max Born was his teacher, and he later came to the help of Heisenberg, or rather a collaboration. Max Born came up with he told Heisenberg, what you are thinking of are nothing but matrices, and they obey matrix multiplication rule. There are 3 groundbreaking papers, first only by Heisenberg, and then with Max Born and Pascal Jordan. In fact, matrix mechanics should be contributed to the whole thing, though it is called Heisenberg matrix mechanics. It's due to both the 3 of them. Max Born and Jordan was his student, Heisenberg's student, I believe. See, June 1925 to September 25, just 3 months, June, July, August, yeah. 3 papers, one in a month. Heisenberg gets his Nobel Prize in 1932. Let me see how much time. Yeah. And enters Dirac now. Heisenberg, in fact, gives a lecture in Cambridge, and Dirac teacher was his host. In fact, Dirac was not there during the lecture. But Heisenberg shares his proof sheets of his June paper with Fowler. And Fowler gives it to Dirac to think about it. And Dirac ponders over the results and comes out with a more flexible form. It's actually Heisenberg was bothered that the diagonal entries were non-commuting. QP minus PQ were non-commuting. And Dirac comes out with the idea that it's nothing but an extension of Poisson bracket. Dirac's results published during 1925, soon after, like it's 4 months from June 1925. 4 landmark papers from October 1925 to February 1926, each month one paper. And Dirac gets the Nobel Prize jointly with Schrödinger. Each of them derived a sole Nobel Prize, individual Nobel Prize. Still, their greatness cannot be neglected or sidelined. Now comes Schrödinger. Schrödinger was, in fact, Heisenberg and Dirac were contemporaries, just 1 year apart. Schrödinger was a bit older, about 10 years or so. He was thinking about de Broglie's wave-particle duality, and Einstein's comments on de Broglie's thesis, and Peter Debay's remarks on connection of the whole thing with the eigenvalue problems of some differential equations. He was initiated by that. See, he was on a vacation, Christmas vacation. Heisenberg was on he was in isolation due to some fever, like our COVID, hay fever. Schrödinger was on a Christmas vacation, and he comes out with his idea of the Schrödinger equation and all that. During that Christmas vacation, it was born on a vacation. And 1926, soon after that, December, and January 1926 to June 1926, 4 landmark papers. And he even establishes that his formalism of quantum mechanics is identical, almost analogous to, almost identical with that of Heisenberg's matrix mechanics. That's during May 1926. Yeah, this period, 1925 to 26, can be called as quantum renaissance or golden era of quantum mechanics. In an article in CERN, never in the history of physics has so much been achieved by so few, only 3 of them in just 2 years. Yeah, it befits their achievement and the significance too. Yeah, here are the 3 of them. Yeah, and Dirac was called the strangest man, like for several reasons, especially because he used to talk very less. And here is one thing that I picked up. 1 Dirac unit is 1 meaningful, his friends and students used to say. 1 Dirac unit is 1 meaningful word per hour on a good day. He never used to speak even for 1 word per hour. On other days, if he had a little bit of mood, if he had anything else to speak about, rather, that too 1 word per hour on a good day. It suits his economy with the words. And here is Dirac's opinion about himself. He says, he was introducing Heisenberg to an audience in ICTP, Italy. He says then, me and Heisenberg were students working on the same problem, that's some quantum mechanics, at the same quantum idea, at the same time. He succeeded where I failed. It looks highly unreasonable that, in fact, Dirac was the, considered his interaction picture is considered as the kind of, whether I can say that or not, it's considered the better version of both Heisenberg and Schrödinger's. Still, Dirac considered himself as a failure because the original idea came to Heisenberg and not to him. And that is the humbleness and giving due credit. What Heisenberg says about Dirac as like he's the strangest man, but despite all that, one of the greatest physicists. He was one of the greatest physicists. Niels Bohr says the greatest human being too, finest human being. So that's about Dirac. Here is a book on Dirac, the strangest man. So like a wonderful book. Yeah, then comes the interpretation of quantum ideas. Born's interpretation, we all know the probabilistic interpretation. Bohr's complementarity principle, and here comes the double slit experiment. Double slit experiment with electrons. Like when it behaves as a wave, it doesn't show the particle behavior, and when it behaves as a particle, it doesn't show the wave behavior. It was voted when it was done with single electrons, I think during 1965. It was voted as one among the 10 topmost experiments. And then Heisenberg's position momentum uncertainty relation and its improved derivation by Robertson, Schrodinger, and Weil. And next comes like von Neumann has contributed a lot to the mathematical framework of quantum mechanics. His contribution should be put on a higher pedestal. And then comes the standard Copenhagen interpretation. I haven't given the year-wise. It was a superposition kind of thing. Copenhagen interpretation is the one that we teach and the most familiar one. And that's what we teach in our MSc and BSc classes. I don't know how much of quantum mechanics is there in only a superficial introduction of quantum mechanics in degree classes, I believe. And the two Solvay conferences, 1927 and 1930, and the very famous Bohr-Einstein debates. Einstein didn't agree with quantum ideas that the behavior of nature is probabilistic. They both had intellectual debates. They both were very good friends, but the disagreement with their ideas, like though Einstein himself is kind of initiated quantum ideas, he was not happy with the probabilistic idea associated. The debates, they were public debates. As I said, they were intellectual debates of highest order. It began with the Fifth Solvay Conference in 1927, continued through 1947, and later they both kind of later there were no public debates, but through letters and kind of exchanges, they still used to debate about their thoughts about what they believe in their idea or interpretation. Yeah, this is Einstein's firm belief that God doesn't play dice. Nature is not probabilistic. Yeah, this is like all of you know. Does moon not exist when we don't observe it? The concept of reality. Even when we don't observe a thing, such a thing exists. The concept of reality that Einstein wanted to be a part of quantum theory. And there comes his physical reality. Can quantum mechanical description of physical reality be considered complete? I mean, this is a beautiful 3-page article which mathematically dense, but such a well-written paper. I believe students should take up, and even teachers should help them understand the idea behind Einstein's reality, physical reality, and the quantum ideas. And then comes Bell. He kind of refutes Einstein's ideas that reality and locality is that there is no simultaneous happening of incidents, and reality, which Einstein like Einstein was very firm on his ideas. And these are the famous. I won't be able to go into these details. And these are like, there's such milestones in the development of quantum mechanics. And this is famous Bell's inequality and violation by maximally entangled states. It's theoretical. Bell shows that for the Bell state, the so-called Bell states, the maximally entangled states, 2-qubit states, his inequality is not obeyed, and it gives the maximum value 2√2. And later, it was a theoretical thing, but through experiments later, it was that the Bell's result is true, and the entangled states disobey Bell's inequality. Bell's inequality was based on the local realism, whereas quantum mechanics, like the ideas are very complex for me to describe in a sentence or two. The quantum mechanical ideas, as proposed by Bell's inequality, were experimentally proved, and quantum states, the 2-qubit Bell kind of states, disobey Bell's inequality, and thereby illustrating that the quantum ideas, the local realism proposed by Einstein, are not correct. And this is a major milestone. And these three people, Aspect, Clauser, and Zeilinger, got their Nobel Prize in 2022. Yeah, now like the father of classical information theory, Shannon's contribution is considered one of the topmost in classical information theory. And later, this was generalized to quantum information theory. In fact, the present quantum information theory can also be called quantum Shannon theory. One among the present day topmost quantum information scientists, Mark White, has written a book, Quantum Shannon Theory. It's a wonderful book detailing the technique of quantum information, and it's a wonderful book. Yeah, so I won't be able to go into the why Shannon's ideas are considered so important, but I can give you some why it was like the comments by scientists during that time, realizing that his contribution is so very important. He was a 32-year-old researcher at Bell Laboratories. During 1948, he comes out with a mathematical theory of communication, and it is considered as the Magna Carta of Information Age by Scientific American, a blueprint for digital era. And see, this was 1948 is Shannon's paper, and transistor was discovered during 1947 again at Bell Labs. Shannon's result was considered more profound and fundamental than transistor. Shannon's, more is the disorder, more is the information, is the idea by Shannon, which was later generalized to the quantum entropy von Neumann. As I said, von Neumann contributed a lot to the mathematical framework of quantum information science. Yeah, now I'm coming to the second quantum revolution. It starts from around 1980. The emergence of quantum computing during a bit earlier also, I will show you. The development of quantum algorithms around 1994. I'll give you the year-wise details. The race to build quantum computers 2002 present. Yeah, here is a chronological detail. This is a paper, 1976, by R.S. Ingerden of Poland. he comes out with a generalization of Shannon's classical information theory. And he's one among the earliest European contributors. And he created a school of thought in Poland that influenced generation of physicists, like the whole family of Horodeskis belonging to Poland have contributed immensely to quantum information science. Michael Horodesky, it's a whole family of 4 members. I don't know whether you have heard of the name. We are all like, their contribution is so much. Yeah. And then, I cannot go away without mentioning Feynman's idea. Yeah, here, just before that, a quantum mechanical model of Turing machine. Turing machine is Alan, like the name goes to, is in the memory of Alan Turing, who is the initiator of the quantum computing, classical computing. Turing machine is nothing but a classical computer. Paul Benioff, US, Argonne National Laboratory, he is the first one to demonstrate that quantum computing can be done. And look at the comment by Richard Feynman. He was so much for simulating physics with quantum computers, quantum processors. He says, this is a comment at Physics of Computation Conference. It's a conclave of engineers, physicists, and mathematicians. Such a conference where ideas got shared. Simulating physics with computers. He says, nature isn't classical, damn it. Look at his words. If you want to make a simulation of nature, better make it quantum mechanical. And he also says it's a wonderful problem because it doesn't look so easy. Feynman liked challenges. He knew that quantum mechanical simulation is the one to go for, and he liked it also because it is challenging. It is challenging, and he is true too. And then chronological details again. Bennett and Brassard, this is one among the quantum cryptographic protocols. I won't be like, cryptography is nothing but a secure communication of information between 2 people. We generally call them Alice and Bob. Much needed. Okay, classical cryptography was there. Quantum cryptography is something the security can be maintained. There won't be any eavesdropping. And if there is an eavesdropping, if somebody interferes in the middle, the receiver will get to know, and the sender can send a different set of information. Another set of information, the original one, so that it goes securely to the receiver. So this is the first protocol, quantum cryptographic protocol, BB84 protocol, it is called. And 1985, David Deutsch is called the father of quantum computing. The name goes to Deutsch. He comes up with a description for a quantum Turing machine. That's a quantum computer. Okay. So, and then comes the Deutsch-Josa algorithm. It's not as much like it's an algorithm which has quantum, it's called a toy quantum algorithm, not very beneficial for practical purposes, but does illustrate the strength of a quantum algorithm, how it is better than a classical algorithm. Yeah, it's one of the first examples that is exponentially faster than any possible classical algorithm. It's considered a toy algorithm. It seems Professor Mallesh has given a lecture on Deutsch-Josa algorithm maybe about 2 months back. Yeah, next coming is the quantum teleportation, the one which catches everybody's attention and so very important, practically also. The idea of quantum teleportation, it's a theoretical idea by Charles Bennett. It's a PRL 1993. And then comes the algorithms. There is a gap from the theoretical to experimental realization. 1994 is Peter Short's algorithm for finding the prime factors of an integer. The prime factor factorization is a very important thing for secure quantum key distribution, and for mathematicians also it is such an important thing, finding the factors of a prime number. Peter Shor's quantum algorithm is one of the, it's called killer algorithm. It is so very powerful. Its significance is it's of the top order. And then Grover search algorithm, and here is it's a quantum database. Like if you are given a series of phone numbers, how do you identify a number that you want? A classical algorithm needs a root n number of searches, order of root n, a root n supremacy over the classical algorithms was given by Grover search, like lesser searches. I mean, what I should say is lesser number of searches through Grover search, whereas classical algorithms, and it gives a quadratic speed up also. You can find out the number of your choice. It's not just phone numbers, any stack of books or any such thing where you can identify the book of your choice. Grover search algorithm is the best algorithm, quantum algorithm to do that, better than classical algorithms. And then comes Anton Zeilinger, the Nobel laureate of 1922. He comes up with, okay, what happened? Yeah, I myself not being able
it's there on the top.
Yeah, it's there on the top. Yeah, the quantum teleportation, and it's a first demonstration of quantum teleportation. Later, several people have done it. I haven't given the details of how many have done it. I can just mention it like I say. And 1999, a superconducting qubit can be superconducting circuit, a Josephson circuit can be used as a qubit. Japanese scientists, they come out with this idea. And then comes the 5-photon entanglement by the Chinese group. 5-photon entanglement is important because like I haven't told about quantum error correcting codes. More than 4 qubit entanglement is needed for quantum error correction codes. Till then, only 4 qubit entanglement was experimentally established. 5-photon entanglement is therefore a significant development. And again, this quantum teleportation over, like it's about 150 kilometers by Zeilinger et al. And I'll show you a picture later of this teleportation. It's a photonic, like transportation of a photon over 150 kilometers. And here comes the, like, as I said in this thing, here comes the race to build quantum computers. The first one by rather, I shouldn't say, there are several in between contributions, developments, etc. D-Wave is the one significant thing to be mentioned. It's a Canadian company. They use the so-called annealing qubits, which are not considered so good, but it goes, like presently it runs up to 5,000 qubits, I believe. Not a gate-based quantum computer, quantum processor it is, but still it does quantum tasks. And another 2011 and 2012, these are kind of startups, I believe, yeah, companies. It's a software company based in Vancouver. They come up with the dedicated quantum computing software. And again, here comes the qubits, which are gate-based and all. So like these are details which probably needs to be described in much more detail. I'm only giving a bird's eye view. And 2014, and the error-free quantum teleportation of a qubit over a distance of 3 meters. And this is by a group, Netherlands group. And here again, yeah, this is over 1,400 kilometers from ground to ground only, using a satellite, using a low Earth orbit satellite. A satellite sends 2 photons, entangled photons, to the sender and the receiver. I shouldn't say the one who sends the information, and well, rather not the information, a qubit itself. I'll come to, if time permits, I'll come to the teleportation protocol. It's a transportation of a qubit from one end to the other, from Alice to Bob. I think this is 1,400 kilometers is the greatest distance that has been experimentally. Yeah, this is a picture showing the development of the quantum in 1900, 35, 64, and 70s. And as I said, ion trap quantum computers, Shor's algorithm, Grover's algorithm. I hope you can just see this. Yeah, there are several stars. Rigetti Quantum Computing is one among the topmost software companies. D-Wave and the Transman superconducting qubits. The IBM uses Transman superconducting qubits. Yeah, up to 2022, the developments are fast-growing developments in the quantum field. Especially this year, it's the International Year of Quantum Science and Technology, and lot of funding is pouring over to every, you might have heard about this quantum roadmap, and about 1,000 crore contribution by the Karnataka government to the quantum skill development, etc., etc. Skill development is one part, quantum computing, etc., etc. Yeah, I don't know how much time I'm left with.
5 minutes. 5 minutes more.
5 minutes. Okay, okay. I don't think I can go into any of these details. These bits versus qubits. Yeah, these are all familiar to you. And qubits are 2 levels of a quantum. An atom, a two-level atom, ion or whatever. Photon is also a qubit with its horizontal and vertical polarizations are the 2 levels that are under consideration. These are the fundamental building blocks. And for a quantum computation, the superposition principle and quantum entanglement are the major resources for, and that gives the quantum supremacy. And whereas I can only have 1 and 0, head or tail, in the case of classical computation, I can have an infinitely many superposition as given by psi is equal to C10 plus C21. Here is the pictorial demonstration. And the quantum supremacy comes because there are 2 to the power of n possible states for n qubits, whereas at once, I think this example, for a classical 3-bit system, it's only either one among the 2 cube states, whereas my quantum processor can be in one among the 8 states. More numbers, more information, more possibility. For example, 2 to the power of 50, and it is the capacity exceeds that of the largest conventional classical computer. Supercomputers, like leaving aside the supercomputer, but there are tasks that cannot be done by a supercomputer. Quantum supremacy is a classical computer cannot perform some tasks. Only a quantum computer can do, and such is the speed up, etc. is one thing. There are tasks which cannot be performed by the classical computers. Is the thing that is the motivation. Motivation are several. One of the quantum supremacy that I can mention. this quantum entanglement is nowadays, it's a household word. So you can, this is a nice thing. A set of gears moving in tandem so that a movement of one results in the movement of the other. And it's such kind of a thing. Entanglement is such kind of a thing. If you change the state of one, the state of other two changes, no matter how far away they are. Yeah, this is something, yeah, I think I can go up to this. Here are some details which you may be interested. I think, yeah, I can go into these details. There are several kinds of qubits that are presently being used. Superconducting qubits are the most prominent among them. As I said, Josephson junctions in superconducting circuits. Transmon qubit is used by IBM, Google, Rigetti, etc. Yeah, the scalability is something you can go up to many qubits, but still not lose the information, coherence, and etc. It's like scalability is most important for building quantum computers. When you have more qubits, the interaction becomes more, noise comes in, and you lose coherence and the ability of quantum computers to perform. The scalability is one thing. Even if you have more number of musical instruments, you retain the quality of the musical this thing. That is the idea. I mean, that's, I can say it's kind of, it's an example for scalability. Though you have more number of musical instruments, if you can retain your quality of music, then the concert is a scalable one. Here too, if you can have more number of qubits are definitely needed for quantum tasks, but more number of qubits should not hamper the process, and scalable fabrication is much needed. And with superconducting qubits, one can do that. That's what is the strength. And superconducting qubits, as we all know, it requires dilution, a lower temperature and difficult to maintain. And IBM's roadmap, IBM uses transmon superconducting qubits. They want to go up to 10,000 qubits by 2026. In fact, we have worked with their cloud computing platform, IBM, with 127 qubits. And presently, it seems they have gone up to 1,121 and 1,386. And this is the roadmap for IBM. More and more qubits, more and more power. The second is the drop-dion qubits. Yeah, drop-dion qubits, we all know, like we need the tweezers to move them over and trapped in with electromagnetic fields. These are examples of ions that we can use, etc. These have long coherence times. They can retain their coherence for longer times, but limitations. I didn't mention about the quantum hardware, the gates. Okay, they are microwave pulses taking one state to another, etc. Limitations are slower gate speeds. Yeah, I'll just go through this. Yeah, these are the startups, trapped ion platforms. As I said, the scalability is less. They operate only in the 50 to 64 qubit range presently in comparison with the other 1000, etc., etc. Neutral atom qubits, these are also trapped in optical tweezer. Rydberg atoms also, Rydberg states also, Rydberg atoms, rubidium, cesium atoms, etc. Here, the limitation is the complexity of laser control. There are strengths, one can have them along 2D arrays. The ones who are working with Rydberg atoms are atom computing, sorry, there is a spelling, Pascal, about 1,000 qubits, their quantum tasks. Photonic qubits, we like, though we can't say it's a full-fledged quantum processor in IISc, Professor Chandrasekhar's group has a 4-photon quantum processor which generates random numbers, and they have illustrated it too. Also encryption, decryption tasks also it does, but it's again not a gate-based processor and at a lower pedestal. Yeah, as I said, the photon qubits polarization states are the two levels for a qubit. Yeah, there are strengths and limitations, and PsiQuantum is targeting a million qubit photonic quantum computer in a few years, in a decade or so. And these are quantum dots, another kind of qubits that are being used, silicon quantum dots. And they're difficult to fabricate. Precise nanofabrication is needed. Scaling is also kind of difficult. Strength is that it is semiconductor industry is fast growing, fabrication is possible, etc., etc. And these are envy centers. Envy centers are much helpful for quantum sensing and metrology. Professor Kasturi Saha's group in IIT Bombay are doing the quantum sensing and metrology work with the envy centers. Yeah, these are the strengths and difficulties. And these are the most promising kind of qubits, topological qubits, still not realized in the experimental stages. The topology itself helps in the scaling and error correction, etc., etc. Noise, we can protect the qubits from the noise. We can have more qubits, etc. This it's still in the experimental stages, and if it gets realized, we can have a big leap in the quantum computing tasks. Yeah, I don't think I can go into the mathematical details.
Running out of time. Time is also coming to a close. Please summarize.
Yeah, that's what. Yeah. I'll show just a picture of the teleportation. I had a quantum teleportation protocol as that could be explained to a student, but like what I can only say is, yeah, this is the teleportation, photonic teleportation performed by Zeilinger et al. About 143 kilometers from where to where, the details are here. It's a 2012 demonstration, and they have also performed in the same experiment itself entanglement swapping also. Entanglement swapping is another important thing to be experimentally realized. Swapping is that if you have two entangled states, say AB and CD, you can generate, if you can generate entanglement between A and B, AB and CD are your entangled states, entangled qubits. If you can generate entanglement between A and D, then it is called entanglement swapping, much needed for the quantum internet, quantum key distribution, etc., etc. There are multi-nodes are required, and if you go on swapping the qubits, the entanglement like between the qubits, then you can go for further distances, and which is very helpful for secure communication as well as quantum internet. Yeah, which is in the making. IIT Madras is at the helm of affairs for quantum communication. It seems they have developed a quantum internet in the small region between their own campus, etc., etc. They are thinking of having a quantum internet. It's called Makan, metro area quantum access software. It is called quantum access network. It's called Makan. And they even want to have an internet network between Bangalore and Chennai. They are doing it with the help of Bharat Electronics, I heard. IIT Madras is at the helm of affairs for this, and this National Quantum Mission is spearheading the funds, etc. needed. Let's see where it, like whether we can have an internet, quantum internet between Bangalore and Chennai. let's see. Let's hope for the better in the quantum era. Thank you.
Thank you very much, Dr. Sudha, for a very informative talk. Now there is time for some questions and comments. Anybody would like to ask, they may raise their digital hand and then ask. Okay, one by one, please, and be brief. Okay. Yeah. Anybody would like to ask? Okay, I will begin with a simple question. You mentioned about
Please, sir.
5-photon entanglement achieved by Chinese.
Yeah.
Could you explain that a little more about how they can achieve 5-photon entanglement?
I don't know the technical details of it. See, generating entanglement between, see, multi-qubit entanglement is a thing. In fact, theoretically also, we don't have a proper metric to quantify multi-qubit entanglement. This is an experimental generation of multi-qubit entanglement. Experimental generation. I don't know the experimental details. Probably I'll like in the present era of ChatGPT, etc. Yeah, with a click we can get the details, but I haven't gone into the details of it. But what I know theoretically is,
I think it is a photon polarization entanglement, not a non-local. But its significance of 5-photon is that if you have 4 photons, you don't have error correction. That is up to 4 photons, you have to live with noisy error. So how they connect each photon with another to create entanglement is through some gates, C0 gate and some H gate kind of things in the photonic platform is what can be said, at least.
Okay, thank you. We'll move on to other questions.
Sir, I have one question.
Please ask. Okay.
Madam, it's a nice lecture that you have rendered. My question is, quantum mechanics is all about the probability. If you have a probabilistic approach, obviously the result will be having some error. How does this quantum computing and all that will have the error, and how this probability reflects on the error?
Actually, probabilistic, I can't say it's an error. It's the quantum science itself. It's like we go with the expectation values. The results of measurements are expectation. The noise or errors that we mentioned here are due to interaction of the quantum systems with the surroundings. This is not a probabilistic error. The whole quantum, the idea of quantum mechanics, which Einstein was not happy with, is that the nature is probabilistic. You can't say it's it's in one, how can I say? Probability is not an error. Probability is not an error. That much I can probably definitely say with certainty. I don't know whether I have answered your question, but the errors that we mentioned in quantum computing is due to noise, loss in decoherence times, etc. Interaction with the surroundings, not a probabilistic error.
Okay.
I have a question.
Okay, please ask.
Madam,
Yes,
can you just give an idea of what slits in time? We have a double slit experiment where we have 2 slits in space.
Yeah.
Very recently, some people speak of slits in time also produce a kind of a superposition.
Difference in time.
2 slits in time.
Slits in time. Haven't heard of it. So can you give me more details, like whether you have gone through some, where you have come across or read something?
I think it's in MIT. In MIT, last 2 months back, they have published a paper.
Oh, I see.
Yeah.
I need
my doubt. No, okay, madam. My doubt is.
Vishal is here and probably.
Okay, my doubt is.
Urvashi Sinha has prepared some kind of a comb, frequency comb or something like that, where you can have time like entanglement also.
Exactly, frequency comb.
It is there, but experimentalists can answer these questions better.
No, not that, madam. I wanted to just know. We speak of superposition when you speak of space, isn't it? Something can be here, some probability. Like that, can we think of superposition in time also?
Yes, it can be thought of.
Okay.
And
Then
also, I may say, I may give you an analogy.
Mhm.
It is something like when you have interference in a slit. And also, if you think about classical light itself, Michelson's interferometer has temporal time delay. Path difference comes because of temporal delay there. So similarly, one can think of it. And there are a lot of thoughts on Bell's non-locality. You have something called as Leggett-Garg inequality, which talks about temporal correlations. These are
That's
developed.
great.
Okay.
Thank you, madam. Thank you.
Any other questions?
Sir,
Yes, sir.
I am Jogad. I think Madam has given in detail several types of qubit, including silicon dot and topological and all these things.
Yeah.
I think, Madam, nowadays only quantum computing they are using silicon dot only, or some other quantum materials are using.
No. As I said, superconducting qubits are used by IBM, Google, etc. There are advantages and disadvantages. Photonic qubit and in TIFR, Professor Vijay Raghavan's group, they have developed a 6-qubit quantum processor. It's a superconducting qubit. They are superconducting.
Some people they are using spin glasses also.
Spin glasses.
Spin glasses.
Again, I should intervene here. There are different verticals in the quantum mission. It is one is materials, that is use of materials to have quantum computing. Which material is better? So far kind of developing. So what you are mentioning as spin glass and all, they come under that kind of a thing, which is still being tested.
Explored.
So which material will give us a better detail? That kind of a thing.
Okay,
So
thank you, sir.
We'll move on to next question. Next
Yes,
question.
sir.
Professor.
I have two questions, sir. One is, of course, this when it comes to this photon entanglement, suppose I make 100 attempts, what is the success rate, madam? Anything like that?
I didn't get you.
No. For example, let's say I'm doing experiment on quantum entanglement. Let's say two photons separated by, photon entanglement. Two photons separated by some distance and all that. Suppose I make 100 experiments or observations. So every time we observe that entanglement, or any success rate is there? Sometimes I fail and things like that.
If you
probably he wants to know how
the probabilistic nature, probably it comes in. There may not be the same amount of entanglement. When you observe, it's kind of an ensemble you are meaning, right?
So probably
an
what
ensemble of qubits, ensemble of photons, to like here separated by a particular fixed distance. If you observe 1,000 of them, let us say, you are asking whether there will be the entanglement, the quantification of entanglement is the same in all the 1,000 qubits. You are asking 1,000 photons, 1,000 pairs of photons, right?
No.
Okay.
No, what he means is how long will this entanglement continue, or how long anticipated if you have 1,000 photons. Maybe that is what he is.
No. Sir, his question is,
okay.
Suppose you generate 1,000 pairs.
That's what,
Do you get entanglement with all the 1,000 if you do? That's what he says.
Success rate, that's what I was.
Success rate, that's what he asks.
Do you not, are you meaning that you are entangling 1,000 qubits?
No, not like
1,000
that.
pairs?
Send one pair by pair, 1,000 pairs.
Yeah.
Every time, are you sure you will get the entanglement? That is his question.
The same amount of entanglement you mean?
Not amount.
Not amount.
Okay.
Entanglement.
Correlation exists, right?
Please wait for the answer. Please
never
wait.
fails.
Please wait for the answer.
If you have a setup, like this is what I feel. If you have a setup in which you generate entanglement between two photons, if the setup is same, if you can generate another pair of, like there, I don't know what you mean by success rate. Success rate is something which if the process, through which you are generating the entanglement, if it is the same, the success rate shouldn't matter. The success, like, it creates the same amount of entanglement.
I should say,
if
we have a factory of producing photon pairs, it will succeed, provided our factory has some defect or my detector has some problem.
System, yes.
So it depends on specific detectors, specific instrument problems, not in quantum mechanics.
If you have the same system, ideal system, you get the same amount of entanglement and the success rate is 100%.
Okay, we'll move on to other questions, please. Any other questions?
Yes.
One more.
Please wait. You have taken your time, so other people should also.
Okay.
Okay.
So shall I ask, sir?
Yeah, please go ahead.
Madam, actually, date-wise, you have taken so many names. I thought that you would have taken the name of our boss, SN Bose.
SN Bose.
SN Bose. Because SN Bose was the one who derived Planck's quantum theory, quantum mechanically.
I completely agree with you.
Yeah, you would have definitely used his name.
Exactly. Actually, I had it in my earlier presentation where only the development of quantum science and just entering the quantum technology area, I had SN Bose in a greater detail. I couldn't do it here because I was to rush from science to technology, this thing.
No, you used so many names, no, because he was the one who derived Planck's quantum theory quantum mechanically. Because Planck himself used classical theory to derive his quantum theory.
Statistical mechanics. Yeah,
that's true. One more question, sir. One more question.
Wait.
Can't deny.
Yeah. Okay,
little elaboration on Bell inequality, madam. Bell inequality.
It will take a lot of time. It will take a lot of time. Maybe
Bell's inequality takes a lot of time, definitely.
1 hour topic. Okay. Any other question? Okay. If no other questions are there, I request our General Secretary, Professor Nagaraj, to propose a vote of thanks.
Thank you, madam. In fact, you have brought from 1900 to almost 2025, and history starting from the Planck's quantum theory, and then Wien's law, Rayleigh-Jean's law. All those things you have covered in just 1 hour. In fact, most of the names which we have not heard also you have brought in. Thank you very much. And it is a nice presentation about this quantum science and technology. Of course, the technology part also you have given in brief, but I think that you need another class for giving us a lecture on quantum technology part. So thank you very much, madam. Thank you very much.
Thank you, sir. Thanks for the opportunity. The whole of KPA. The whole of KPA. Thank you very much.
From KPA, we also thank Dr. M.K. Raghavendra, who is providing the Zoom platform every Sunday. And we also thank from KPA, S.V. Raman. And he is actually making the students to join in YouTube. And of course, Professor Cogley, he is doing almost every Sunday. And there are many other invitees in addition to our KPA members. From KPA, we thank them. Again, we welcome them to attend other lectures also in the coming days in addition to this. And again, I thank all the members who have joined this platform to listen to Dr. Sudha. Thank you very much. Thank you very much.
Thanks a lot.
Thank you, sir.
So we'll be having another lecture next Sunday. Please join us on that day. I invite all of you and your students and associates next Sunday, that is 24th August at the same time. So now we are closing the meeting. Thank you very much for participation. Thanks a lot. Okay, we are closing.